try to create here to get an idea about how science, mathematics, engineering, whatever it happens to be, is used in places that you don't often see in class. So hopefully you enjoy the presentation that we have here today. The presentation that we have will be presented here by John Flood. He's an assistant professor here of biology. He got his degree at the University of Wisconsin. What was this?
Stevens Point.
Stevens Point. And then got his degree in materials chemistry at the University of Colorado Boulder. He teaches a variety of classes here from chemistry 1210 to 2210 and 2220, right? Yeah, so if any of those classes happen to be anything that you think you may be going towards, that's fine. Without further ado, I'll hand it over to John. Just do also know that we will be passing out an attendance sheet here as well. Just kind of keep track of who is here. If you are trying to get credit for our class, we just ask you to put your name, your instructor, and if possible, if you know what class that is, so we can let them know that you were. With that said, take it away.
Thank you, Rob. And thank you, everybody, for joining us here today. I know a lot of you just came in, and so these questions on the screen are a little bit new to you. Also, much like a high entropy system, you guys are very spread out, so it might be a little bit challenging. We have an interaction. You guys grabbed a sheet on your way in today, and without us being as packed as I might have expected when I planned this activity, I'm going to explain how this interaction is going to help us understand energy from a molecular perspective. So I do want to address one thing. This seems like a dad joke. The STEMperature is rising. That's the only dad joke you're going to get today. I'm sorry. But as a chemist, I want to talk to you about what temperature really means, and that means diving into heat and energy from a molecular perspective and looking at how molecules take on heat, energy, and how they transfer that energy. So going back to these questions, I'd love if I could get some hands raised to see if you guys have any input. When you think of heat, what comes to mind? Energy. Great. What else? The temperature. Yeah, your mind goes to temperature when you think of heat. What else? Melting. Love it. All things considered with heat. Was heat a part of your day today? How did heat play a role in the way you got here or the way that you got ready? Your car froze over? Absolutely. It was a very cold morning. And that might actually make us think of lack of heat, right? All of the energy from the moisture in the air was stolen, and it precipitated as frost. There you go. Wearing a sweater because it's cold outside, and now you're hot inside. Any other ways that you guys feel heat, temperature, energy, melting was a part of your day today?
Hot water.
How'd you use hot water? There you go. And then lastly, do you think that you could define hot versus heat? We've had this conversation about hot water, things that are melting, putting on a sweater and getting hot. How would you differentiate these two terms? Interesting. So hot is a feeling and heat is a measurement. Anybody else want to add something to this? Hot is having a lot of heat. Hot is an adjective. Might we say then that heat is maybe a noun? Heat is something, hot describes something. Awesome. Anything else you guys want to add? All right. These were really great inputs. Now, I want to take us first to look at hot. Hot is actually a quantification. Hot is a measurement. We say things are hot or cold, and that means that we're describing their temperature, which inevitably relates to the energy that that thing has. So you see on this left picture, we've got a thermometer at a very cold temperature. We're saying that it doesn't have a lot of energy, and we'd actually be describing the material that's inside the thermometer. Now, typically, that's in some sort of thermal equilibrium with what is outside of the thermometer. So if we know the energy of the material inside the thermometer, then we also know the energy of the material outside of the thermometer, your water or your air. And when you increase the temperature, we say it gets hotter, it's holding more energy, it has a higher temperature. And the scales that you see here are the ones we're most familiar with. Degrees Fahrenheit, used in a very small remote part of the world called America, and degrees Celsius, used everywhere else in the world. But temperature has another measurement that actually helps us put into scale just how big quantifying energy can get. So here I've shared with you some screenshots of a Desmos online calculator calculation. On the left-hand side here, we see 3 different lines. In green is what we call Kelvin. This is an absolute energy scale. Kelvin does not represent energy with negative numbers. Whereas degrees Celsius in red and degrees Fahrenheit in blue can have negative numbers to describe how much energy something has. And that's because 0 has been set as some reference point for us. Degrees Celsius, famously set as 0 degrees Celsius is the freezing point of water. 0 degrees Fahrenheit, totally arbitrary. No, but I'll let you explore that more on your own. Fahrenheit has a story of its own. Absolute 0 is one of the main stakes of the temperature scale for Kelvin. What we say is that 0 Kelvin is when a substance has 0 energy inside of it. That would be the same as negative 273 degrees Celsius. Most of our experience on Earth happens inside of this range on the temperature scale. But as we start to look at hotter and hotter things with more energy, this is a perspective of the Earth at large. The core of the Earth is at about 6,000 degrees Kelvin. That's where there's so much energy that the material that makes up our Earth is very, very hot. As well as 6,000 degrees is the temperature of the surface of the sun. The corona of the sun is closer to 2 million degrees C, and the core of the sun closer to 15 million degrees. Much, much hotter, much higher temperature, allowing for things that can't happen here on Earth. When we get into the tens of billions of degrees Kelvin, tens of billions of degrees Celsius, first of all, you'll notice that the distinction between Kelvin and Celsius seems to fall away. At that point, whatever difference Celsius and Kelvin indicate, these scales are so large, it doesn't actually make a difference. Tens of billions of degrees Kelvin, this is the temperature of most supernova. Supernova are some of the most violent processes in the universe. They include so much energy that matter can actually be fused into heavier forms of matter. The hottest recorded temperature in our solar system actually takes place beyond the tens of billions at the trillions of degrees Kelvin. Anybody want to take a guess at where 5 trillion degrees Kelvin was recorded in our solar system? It's not in the core of our sun, which only gets to about 15 million degrees Kelvin. 5 trillion degrees Kelvin, an insane amount of energy, a very high temperature, was actually recorded at CERN, the Large Particle Collider. That is the highest temperature that we have ever reached in our solar system, and it happened here on Earth in a lab. Absolute 0 is the definition of 0 Kelvin, where something has no energy. Absolute hot is a debated term. and it's often given this number 1.5 times 10 to the 32 Kelvin. That is a temperature at which quantum physics stops working, classical physics stops working. They say that maybe the two forms of physics merge at that point, but the truth is we don't know what happens to physics beyond absolute hot. So that's a temperature where we're not sure what would happen if something had that much energy. Okay, so again, to remind you of some of this scale, quantum computing takes place at thousandths of a degree Kelvin. Very, very cold temperatures, not absolute zero. Outer space takes place usually, or has an energy usually around tens of degrees Kelvin. We live most of our lives ranging somewhere from negative 100 degrees Kelvin to 300 degrees Kelvin. And while it might feel like it got very, very cold this morning, and while it might feel like Utah gets very, very hot in the summers, that is nothing compared to the immense temperature that happens other places in the universe where temperatures get incredibly hot. A question? Actually, I did look into this. Typically, black holes can be incredibly cold. Although it's debated what you might measure in that temperature because matter kind of starts to stop existing inside of that black hole. The outside, the accretion disk, incredibly hot, very, very high energy before it gets pulled into the core of the black hole. So the theory is black holes are actually pretty cold on the inside. At the singularity. Well, if we think about what that energy is, and I'm actually going to try and get us into understanding how that energy manifests inside of matter and material, like how the energy manifests inside of a quantum computer, in our atmosphere, or in a supernova. In the singularity of the black hole, there's not a lot of energy. That matter doesn't have a lot of freedom to do what it will. So we would say that it's very cold, a very low temperature. Thank you. So in order to understand the manifestation of all of this hot and cold, this temperature, we have to get at the core of what temperature we're actually measuring, whose energy we're measuring. So we're going to do a crash course on chemistry. Chemistry is the study of matter and the changes that it undergoes. And matter is largely composed of these three things. Protons, which contain some amount of mass that we say 1 atomic mass unit, and a positive charge. Neutrons, which have roughly the same amount of mass, 1 atomic mass unit, but have no electrical charge. And electrons, which have an insignificant amount of mass compared to the protons and neutrons, but have a negative electrical charge. And so this is the smallest unit of matter. This is our atom. Inside of the atom, we have a dense core that we call the nucleus that has a net positive charge. And outside of the atom, we have what we call an electron cloud, where all the electrons are found. This is a great visual for understanding the components of matter and the buildup of the atom, but it is a terrible representation of what matter actually looks like. For instance, if you were analyzing this, you might think that the nucleus makes up about 50% the size of the atom. If this were drawn to scale, the nucleus should be about 1 million times smaller. You wouldn't be able to see it if the electron cloud was drawn this large. The other misconception you might get from this image is that electrons sit in these nice little circles around the nucleus. One thing this helps us understand is that electrons occupy specific energies. And actually, these electrons are able to move between energies if that energy is transferred to it. But in actuality, an atom would look a little bit more like this. You wouldn't see a nucleus, and you wouldn't see discrete places where electrons are found. You'd find what we call electron clouds. And these clouds resemble waves. That's because electrons, rather than being particles, are truly best described as being waves. And these look a lot like waves that you could make in a pool. I mean, some of them you'd have to be very good at making waves in a pool to make that, but you could see a wave in a pool making that type of a shape. So electrons occupy energy levels. Those energy levels look different from each other depending on the shape of the wave that the electron has. Okay, we're not going to get too deep into the quantum mechanics of all of the matter, but this is the most fundamental piece of our matter, the atom. Inside of those supernovae, inside of stars, protons, neutrons are being fused together to create heavier and heavier nuclei. In the supernova, we get the heaviest of nuclei, things like gold and silver, those rare earth metals. Our star, the sun, currently only creates helium, one of the lightest elements. Stars, towards the end of their life, usually start making iron before they die and explode and create all of the rest of our nuclei. After those supernova, when all of that matter has been created, all of those individual atoms start running into each other. And they decrease their temperature after the supernova. They come to a little bit of a lower energy state, and they start experiencing a phenomenon called bonding. Now, you can understand that at very high energies, at very high temperature, atoms would be dissociated from each other. So inside of stars, atoms don't bond. They're at too high of an energy. But outside of stars, atoms fall into these potential energy wells, where they actually find themselves more energetically stable if they're bonded together. And this should feel intuitive to you, like kicking a soccer ball into a ditch. That ball naturally rolls downhill by gravity. The same thing with atoms. They naturally form bonds just by the energy of their electrons. But again, atoms don't really look like this, and bonds don't really look like this. Instead, they look a little bit more like this. And if you've taken my organic classes, then you would know that this is called molecular orbital theory, where the electrons are not found around one specific atom, but they're found around multiple atoms. And again, we've got this energy gradient that says, if you put too much energy into this system, the electrons will occupy different types of orbitals that are of higher energy, that break the bond, that move the atoms further apart from each other. Okay, so atoms bond with each other because there's some energetic stabilization. And that leads us to larger and larger, more complex molecules. You'll notice along the top here that we've got different types of nuclei. The boron nucleus, carbon, nitrogen, oxygen, fluorine. And not every element likes to bond in exactly the same way. Depending on the element, it has different preferences for what is stable bonding and what is unstable bonding. There's this trend from carbon to fluorine where the atoms prefer to keep more electrons for themselves and share less electrons with other atoms. Carbon is of particular interest to a lot of people because of just how uniquely it likes to form bonds. It loves to form bonds with other carbons, loves to form bonds with all sorts of other elements. It has this unique energetic stability when it bonds to pretty much anything. And so we get a class of compounds that we call organic molecules, those that consist of a carbon chain. Things like formaldehyde, carbon dioxide, acetylene, ethylene. Yes?
The least stable element, or not what is it, but that has the longest life without bonding.
Yes. So if I can repeat the question correctly, which element prefers to bond the least? And that would typically, I think most people would say helium. Helium is our second element. It has 2 protons in the nucleus. And I did skip over some of the nuances of why atoms bond and why they bond the way they do. But helium is very stable when it has its 2 electrons to itself, and it actually, if you look at a diagram like on the right-hand side, helium trying to bond with itself wouldn't know that it's bonded to itself. It would just simply drift away. The 2 atoms would just drift away from each other because they would be at exactly the same energy separate as they would be sharing electrons. So heavier noble gases, things like neon and krypton, are also fairly stable. They don't like to bond to other atoms. But they have at least a better potential for bonding to other atoms. And then even heavier noble gases, like xenon, is known for forming bonds with other atoms. So as they increase in size, the complexity of their electron domains also increases. And all of that kind of feeds back into the stability of whether it bonds or not. Okay, I want to take a second here to point out that you all have a slip of paper that tells you you are a chemical. And I want to show you guys what some of those chemicals look like. So a raise of hands, and feel free to look around the room to see how many other people share this chemical with you. A raise of hands if you are holding something that says nitrogen. Take a look. That's a lot of people. Nitrogen as a chemical likes to bond twice, N2, and those 2 nitrogen atoms share 3 sets of electrons and they keep their own set for themselves. How many of you have a chemical that says methane? Raise of hands. Much fewer. Methane is one of our organic compounds. It's even this chemical that's listed up here. How many of you have a slip that says you are water? All right, about the same ratio as methane. Water, also demonstrated on our slide up here, has oxygen as one of the central atoms. And then our last one, carbon dioxide, a raise of hands. All right, looks like carbon dioxide might be our smallest component in the room here. Carbon dioxide also represented on our slide as one of our potentially organic compounds. These are the chemicals that I'm having you portray today. And in a little bit, we're going to get to an activity where the nature of your element determines the way that you're allowed to increase in energy and share energy. The complexity of molecules gets very large very fast. Because carbon likes to bond with other types of carbons, we start to get these very long carbon chains, which lead to an important class of compounds called amino acids. Amino acids are the building blocks of life. They're what build up your proteins and your enzymes that allow you to function. Another important class of molecules is DNA. DNA is typically thought of as that double helix. That's actually 2 molecules interacting by hydrogen bonding. Each strand is its own molecule because there is an uninterrupted series of bonds between atoms. That creates one incredibly large molecule, possible due to the phenomenon of bonding, this energetic stabilization by sharing electrons. Despite the molecule, all of these molecules share energy in very similar ways. There are 3 ways that a molecule can take up energy. The kinetic energy, the way that it moves. So one of these ways is called vibrational modes. These are where the bonds stretch, bend, wag, twist. We're going to talk more about these vibrational modes. Molecules can also rotate. They can spin around. Molecules can translate, move in a certain direction. Not every molecule is able to do the same amount of translation, rotation, or vibration. For instance, those gas molecules that make up the air that we're breathing, they do a lot of translational motion, rotational motion, but they have very little vibrational motion. Meanwhile, the materials that you're sitting on, those solid compounds, they actually do very little translation and very little rotation. Thank goodness, or they would just translate away from you, or you'd rotate right through them. And yet they can have the same amount of total energy, meaning that these solid materials you're sitting on experience a lot more vibrational modes than the gas molecules that you're breathing. So things that are at the same temperature have the same amount of energy, but they can express that energy in different ways. But molecules are rarely alone. It's important for us to also consider how molecules interact with other molecules. We call these intermolecular forces. This can actually define why certain molecules are able to only vibrate and not rotate or translate, and why certain molecules don't vibrate much, but they rotate and translate like crazy. On the bottom right here, we actually have our weakest type of molecule-to-molecule interaction. And as we move to the left, and then again on the top to the left, we start seeing stronger and stronger types of intermolecular forces. Molecules that have very weak intermolecular forces don't need to have a lot of kinetic energy, be it rotational, vibrational, or translational energy, to break free of the attractive forces to other molecules. That means that they can overcome their intermolecular forces very easily and escape, translate away. Compounds that experience very strong intermolecular forces, it's a lot harder for them to break free of other molecules. And this actually helps us define what molecules experience, which is the phase of the molecule, the phase of matter. We're used to seeing these three phases: solids, gases, and liquids. Solids, where molecules don't have enough energy to break past intermolecular forces and move around one another. They are packed closely together. Liquids, where molecules have a little bit more energy to move past one another, but they stay pretty close by. Those attractive intermolecular forces hold them close. And gases, where molecules have enough energy to escape one another's hold and fly free. So, gases do not experience forces between other molecules. Liquids have enough energy to kind of break free of those forces, and solids are held in place by those forces. Now, this diagram actually adds an added layer of difficulty I don't want to get into, which is pressure. Most of us, every day, experience about 1 atmosphere of pressure here on the bottom. So I want you to analyze this diagram at 1 atmosphere of pressure and imagine what this chemical might be. At 0 Kelvin, the molecules do not have enough energy to move past each other, and they exist at a solid. At about 197 degrees Kelvin, which is negative 76 degrees Celsius, these molecules start to get enough energy to break free of the intermolecular forces, and they escape directly into being a gas. They're no longer interacting with each other at all. Might this be water? Why not? Right. Dry ice, also known as CO2, solid carbon dioxide. And I know you had a question as well. Plasma is a strange definition. It is ionized gases. So actually the northern lights are plasma. You can also create plasma inside of a microwave if you're not careful and you're being dangerous. So plasma is technically a gas, but it's gases that are ions, and so they're also very high energy, but they don't really have a place here. If we were looking at a chemicals phase diagram, and that chemical was an ionic compound, then this technically would be its plasma phase. There's a lot more that goes on here, by the way. This is called a triple point, this is a critical point, and there are things called supercritical fluids. We don't have the time to get into it, which is a bummer. So as you said, this cannot be water because water at 1 atmosphere does not turn from a solid into a gas. We all know that water at our typical pressures will melt first and then it will boil. This is carbon dioxide. Solid carbon dioxide is very cold, but as soon as those molecules of carbon dioxide get just enough energy, there's not a lot of intermolecular forces holding them together. So they break free and they fly away as a gas. Here is the phase diagram for water. Now notice that the y-axis has changed. Now our 1 atmosphere is up here at the middle. And you'll notice again at 0 degrees Kelvin, there is not enough energy in those molecules for them to break free of one another. At 273 degrees Kelvin, those molecules have more energy. That energy is mostly in the form of vibration, but not in the form of rotation or translation. And it's not until 373 degrees that we finally see those molecules completely break free of their intermolecular forces and become gases. Now I want to take a detour real quick to show you guys a visualization of this. Here is neon. Neon is a noble gas which has very weak intermolecular forces. As I increase the temperature in this system, and you can see the temperature with this thermometer here, you'll notice that neon becomes a gas at very low temperatures. Neon doesn't have a lot of forces holding molecule to molecule, which means very little energy. Those molecules escape each other's grasp. As we look at water, at 430 degrees Kelvin, we're seeing water exist as a gas. That would be somewhere over here on our phase diagram. As I drop the energy inside of this system, as I steal energy from the molecules and I drop the temperature, those molecules start interacting with each other a lot more. And you can see that they still bounce and they vibrate and they move a little bit, but now we're sitting within the liquid phase temperature for water. So they're able to move around, but they can't really get past each other. As I drop the temperature even more, you'll see that they stop vibrating quite as much. Their translation and rotation pretty much entirely stops, and they become frozen in place, unable to move past one molecule. Okay, so this is our understanding of energy inside of our molecules. Now, let's get back to this original question, which was, what is hot versus heat? We now understand what hot means. Here, the molecules are moving very little. They have little amount of energy. Here, the molecules are moving a lot more. They have a lot more energy. Heat is the transfer of this energy. And heat predominantly takes on 3 forms: conduction, convection, and radiation. One thing I want to point out is that different phases of matter are being named here. Solids are responsible for the conduction. The conduction of heat from a fire to your hand is conducted through the solid metal of the fire poker. Or from your tea to your hand, that conduction is made through the metal of your spoon. Solids will vibrate into each other and pass that energy along until all of the molecules at low energy have gotten up to high energy. Convection here is fluids, gases, and liquids, because those molecules are able to move past one another. Now they're bumping into each other and taking that form of energy that they have in rotational energy and translational energy, running into neighboring molecules and passing that energy along. Radiation stands alone. Radiation looks nothing like our other 2 forms of heat transfer. Once again, Conduction and convection is taking all of that energy that a molecule has in its vibration, rotation, and translation and running into another molecule, sharing that energy along. Anyone who's been in a car crash, and we're in Utah, so I know at least some of us have been in a car crash, you know what that transfer of energy can feel like, right? Radiation, on the other hand, is what we colloquially call light. Electromagnetic radiation. And you'll hear in that name, electromagnetic, light consists of two parts, the electric field and the magnetic field. They impact one another. At very high electromagnetic radiation, we transfer high amounts of energy. At very low electromagnetic radiation, we transfer low amounts of energy. And despite the visible spectrum making up a small part of the full light spectrum, we're pretty familiar with all of these different ranges of energy transfer. All of us that use our cell phones to transmit information are using radio waves. All of us that heat up our food in the microwave, we're actually using electromagnetic radiation to start rotating water molecules. As we increase their rotational energy, they can bump into other molecules and transfer that energy to the rest of the food. We all use visible light produced by our lights in order to see. And of course, X-rays in medicine and gamma rays to make Hulk. So, electromagnetic radiation, a very common, a very prevalent form of energy transfer, one that maybe we're not so familiar with thinking about actually transferring energy. If you take, for example, an experience that we're likely all sharing right now, which is light bulbs above us having electrical current pumped into them, high energy, their thermal energy is increasing, and the electrons inside of their systems are then falling to low energy states and releasing that difference in energy in the form of electromagnetic radiation. That radiation hits the molecules inside of your eyes. Because it is electromagnetic radiation, it interacts with the electrons in the molecules in your eyes, and that energy is transferred to those molecules, to your nerves, to your brain, transferring energy from an electrical current through a light bulb into light, into your eye, into your brain. All heat, because it's all transferring energy. I want to bring this back a moment. Remember earlier we said heat was really associated with a lot of hot things, hot water, hot days. It doesn't need to be hot, does it? Heat can happen at any temperature as long as we're transferring that energy. Let's look at some other ways that electromagnetic radiation correlates with hot. This is something called black body radiation. Our sun is considered a black body, despite the fact that nothing seems black about it. That's because at very high temperatures, materials that would otherwise be black have their electrons moving between energy shells, and those electrons then fall from high energy to low energy and release that difference in energy as electromagnetic radiation. The higher the temperature, the higher the energy that is expelled by that body. So our sun sits somewhere around 6,000 K at its surface, and we get a lot of visible light, but we also get infrared light, and we also get ultraviolet light from our sun. Our light bulbs are sitting somewhere around 3,000 degrees Kelvin, and here we get mostly white light, but if you've ever gone up and grabbed a light and it felt hot to the touch, that's because it's also, it has a lot of thermal energy, and it's releasing some infrared energy as well. A really cool example of how electrons can transfer energy, especially through electromagnetic radiation, again happens at a very cold temperature. These are the northern lights. The red, green, purple, and blue, all different wavelengths created by different electrons moving between different energy levels. Specific energies of light responsible because of specific energies that electrons transition between. And the northern lights, I think a lot of you would agree, not happening in a very hot place, happening at our outer atmosphere, pretty cold. So here's a question I have for you all. If the northern lights is caused by atomic oxygen and molecular nitrogen having electrons fall from high energy to low energy and release that difference in energy in the form of electromagnetic radiation, how did the electrons get to high energy in the first place? I don't know if you've noticed, but every time we see the northern lights, there's usually a heads up. People observing the sun will reach out and tell us, the community, that, hey, there's a solar storm happening, and the sun has just released an insane amount of energy, and it's coming right towards us. So our magnetic field channels some of that energy into the poles, and those highly energetic particles from the sun ram into oxygen and nitrogen in our upper atmosphere, transferring that energy into their electrons. And then those electrons fall down in energy, and we get to watch it as this beautiful light in our upper atmosphere. Very cold, very much heat. Let's look at the other way that energy can be transferred between matter and electromagnetic radiation. These are both forms of matter emitting electromagnetic radiation, but electromagnetic radiation can also be absorbed by matter. And it's absorbed in the same way. Electromagnetic radiation interacts with the electrons inside of bonds. We saw this graph earlier, where two atoms come together into an energy well because it's energetically stable for them. But at any specific energy, those atoms are actually always moving in and out, compressing the bond and expanding the bond. With the right amount of energy, a very specific amount of energy, those electrons can be moved into even higher energy vibrational modes. Now, this graph on the right actually shows us specific energies of light on the x-axis, and then a roadmap of different unique types of bonds. Unique types of bonds meaning things like nitrogen-nitrogen triple bonds, carbon-hydrogen bonds, oxygen-hydrogen bonds, carbon-oxygen double bonds. What we understand about the way bonds absorb energy is that specific bonds absorb specific energies. And so we can transfer specific types of heat to our molecules. This is actually the type of spectroscopy that astronomers will use if they look out at a planet, whether it be in our galaxy or in other galaxies, and say, this planet seems to have organic material. That's because they're looking at the light transmitted through the atmosphere of that planet, and they can see what light is being absorbed. If specific energies of light are being absorbed, that tells us specific bonds are present. So here's the way that those bonds will actually transfer energy, and here's where the talk starts to get a little bit more interactive. These are the stretching and bending modes of different types of bonds. Stretching of bonds can happen symmetrically. These bonds are compressing and expanding symmetric to each other, but stretching can also happen asymmetrically. And so I'd like you guys, if you have the space, you may need to go a little bit higher up so you don't hit your neighbors. Do these with me. Let's become molecules. Symmetric stretching. Great job. Asymmetric stretching. Woohoo. The in-plane bending looks like rocking side to side and scissoring in and out. And now the out-of-plane bending happens as wagging back and forth Sorry, I know I started on the bottom there. Wagging back and forth and twisting. One bond in, one bond out. Congratulations, you have all just absorbed and transferred energy. You are all now heat. So I want to take this application to our atmosphere. I'm sure a lot of you saw the title of this talk, The STEMperature is Rising, and maybe thought that this talk would have something to do with climate change, global warming, and the way that the temperature of our planet is increasing. I'm sorry to say I'm not very well educated in exactly the nuances of climate change and global warming, but I can give you the molecular perspective of what's happening. And you all are going to model it in just a minute. Here is another simulator from that same website that I showed you guys before. And I did mean to actually highlight this website a little bit more. This is called the Physics Education Technology, or PhET. And these are a number of different simulators that help you understand all sorts of things about physics, chemistry, and biology. So here, what we're looking at are different molecules and different types of light. Earlier, I told you all that if you've used a microwave, you have created rotational energy in your water molecules. You know what? I didn't realize there'd be sound, and the sound is a little bit unnecessary and distracting, so I'm going to mute that if I can. So you'll notice that this light coming out of this little flashlight is microwave, and it makes the water spin. Not all of these molecules will interact with that electromagnetic radiation. Oxygen here, not rotating inside the microwave. Nitrogen, not rotating when exposed to the microwave. This is why we can heat up water inside of our microwave, but we're not necessarily heating up the nitrogen gas that's sitting around all of our water. Different molecules interact with different light in specific ways. Let's look at nitrogen dioxide and start to give it some ultraviolet light. Whoops, did you see that? Our nitrogen dioxide fell apart. Nitrogen dioxide that sits in the upper atmosphere interacts with ultraviolet light, decomposes. Here's another molecule interacting with ultraviolet light. This is ozone, which also plays an important role in absorbing ultraviolet light from our sun and making sure that it doesn't hit lower parts of the atmosphere. Other molecules, pretty inert to ultraviolet light. No reactivity. Nitrogen, the major component of our atmosphere, inert to ultraviolet light. No interaction. Here we see visible light. Now, visible light may not have any interaction with a lot of these molecules. The energy in visible light just doesn't meet the requirements for translational energy, vibrational energy, translational energy. The only difference here is nitrogen dioxide. Nitrogen dioxide is a predominantly red gas. It's red because it's absorbing parts of the visible spectrum, but not absorbing red light. A similar phenomenon here, chlorophyll, the most famous part of a plant, that green stuff, it absorbs mostly red, reflecting the rest of the green light that's hitting it. Now let's look at infrared light. Back on that electromagnetic radiation spectrum, infrared actually had a picture of a human, a glowing human that wasn't the Hulk. That's because infrared energy correlates with thermal heat, the movement from bonds. That absorption spectrum that I showed you earlier, specific bonds that absorb specific energies of light, those were all stretching frequencies inside of the infrared spectrum. So nitrogen dioxide absorbs infrared light, turns it into vibrational modes. Methane absorbs infrared light, turns it into vibrational modes. Carbon dioxide absorbs infrared light, turns it into vibrational modes. Nitrogen, no interaction. Oxygen, no interaction. Water, vibrational modes. So here's what I want us to demonstrate together. I would like for you guys to be the molecules on your sheet. If your sheet says blue, I want you to absorb through asymmetric stretching. If your molecule says green, I want you to absorb by twisting in and out. If your molecule says red, I want you to absorb by scissoring. These generally reflect the ways that each of those molecules actually absorb energy. If you are yellow, that means you're nitrogen and you're not absorbing any of this infrared light. All right, this might help if you stand up. The other aspect to this interaction is as you absorb energy, you're going to transfer it to other molecules, and you yourself will move to lower energy. Because not all of us are very close, you may have to pick someone and throw your energy at them. At that point, that person should move into a higher vibrational mode. Maybe you can just rock. And you should move into a lower vibrational mode. All right? So you're going to be transferring energy from your vibrational modes to your lower vibrational modes. All right, ready? Yellow. Wait, no. This is supposed to be red. Look around you. How many people are scissoring? Not a lot are absorbing through that scissoring motion. Now, transfer your energy. All right. Now, those people that had scissoring motion are now moving a little bit less energetically, and they threw their energy to other molecules who are now moving more energetically. All right. Water, absorb your energy through rocking. All right, now run into another molecule in the atmosphere. Transfer your energy. If you're noticing, a small number of molecules are absorbing, but after they transfer their energy, more molecules have energy. Lastly, methane. This one, I think, yeah, we are twisting. All right, methane, you're twisting, you've absorbed your energy, now transfer it to another molecule in the atmosphere. We had, I think, 2 people twisting, and now we've got 5 people twisting. You are all transferring heat. Okay, on the count of 3, have you guys noticed yellow, nitrogen, you didn't absorb anything? That's because you're not interacting with the infrared light. So you need to be looking for a molecule to steal energy from. This time, carbon dioxide, methane, water, all of you absorb energy. Nitrogen, steal some energy from those other molecules. I think we've got enough that the whole auditorium is now rocking. With just one flash of infrared light, I have transferred energy to specific molecules and then dissipated that energy across the rest of the auditorium. Now, this is global warming. A small number of molecules in the atmosphere are absorbing the infrared light that the Earth is radiating out. That light should just transmit right through the atmosphere, but it gets caught in vibrational modes in the molecules, transferred to other molecules that wouldn't have otherwise caught it, and warms up the entire atmosphere as a result. And that warming of the entire planet, despite being such a small change on the large scale from absolute zero to absolute hot, has very important implications in our everyday lives. The way that our proteins fold changes at those different temperatures. The way that oxygen dissolves in water changes at those different temperatures. There's an impact by absorbing energy with a small number of molecules and changing the global temperature by such a small amount. And if you've thought about the climate crisis before, I hope that now you have a bit of a more intimate connection with how that energy transfer is actually happening. Thank you. I think we have about 5 minutes if there are any additional questions that anyone would like to ask. here?
I saw a backwards line on the water graph a few slides ago. I was wondering, that might have some sort of strange case scenario.
Can you tell me which graph?
Back up more there. With the black line seems to have a slope that goes backwards.
Oh yeah. Why does it move backwards? Well, this is a relationship between temperature and pressure. We didn't talk much about pressure, which is basically just the force that those molecules are experiencing. I don't know that I have the background enough on the mathematics of it to explain it to you, but all I would say is that at that point, there's an inverse relationship between the pressure that a molecule experiences and the energy that it has along the phase that it will exist in. You're noticing there's a direct or a proportional relationship. As pressure and temperature both increase, this other line continues in a positive direction, whereas this other line tends to go backwards. I think the only thing I can say there is that it's an inverse relationship rather than a proportional relationship. Sorry that I don't have a bit of a more in-depth. We can talk physical chemistry though after this. Killian. What on earth is giving off infrared? Well, pretty much anything that has absorbed sunlight. That would be plants, humans, blacktop, sand. All of those things can absorb light and then emit it at a lower frequency as infrared light. Snow may give off a small amount of infrared, but snow predominantly reflects the visible light that it is hit with. It's white, so it doesn't absorb any of that light. A limit to how big or small. Actually, this is part of the problem with absolute hot. At absolute hot, the wavelength that a photon of light would need to be if it was being emitted by an object that had that temperature, the wavelength of light would exist below the Planck length, and the Planck length is like times 10 to the negative 32 meters. It's an incredibly small distance. It's the smallest distance we understand quantum mechanics obeying. So the wavelength would be smaller than that, at which point we don't know what would happen. So there is a minimum limit to how small it can be, and that would be at absolute hot. I don't think there's a maximum limit. I think you're probably seeing the longest possible wavelengths in the cosmic background radiation. That's light that has been dissipating and traveling for ever, since the beginning of ever. And so that would probably be the longest wavelength, but I don't think there's a limit to how long that wavelength could be.
How does the electronegativity of a molecule affect how it absorbs energy?
The electronegativity of a molecule doesn't inherently affect how it absorbs energy, but it can affect the way that it bonds, the things that it bonds to, and then in that way, the bonds might impact what energy it absorbs. The most electronegative atom, fluorine, likes to bond to other atoms of fluorine just once. Now, those won't absorb a lot of electromagnetic radiation unless it's exactly the right amount to split that covalent bond. Whereas hydrofluoric acid, HF, or pretty much any time you've got a bond from something less electronegative to fluorine, you can create a stretching of that bond just by showing it infrared radiation. So electronegativity, not a direct impact until it's in a bond. Did you want to add to that?
No, I wanted to ask a question. What class would someone take to learn more about this?
God, I don't know. Well, let's see. A lot of this, raise of hands if you are in my Gen Chem class or took my Gen Chem class. We talked a lot about this in general chemistry, the electromagnetic spectrum, and the way that electromagnetic radiation interacts with light. We also talk a lot about phases. In my lecture this morning, we talked about solids, liquids, and gases and the intermolecular forces that hold them together. Of course, in class, we get into it a lot more, and we talk about what are the molecules, why do they have those forces, all that kind of stuff. In organic chemistry, we use infrared absorption a lot. Those of you in the organic chemistry labs, you guys use infrared absorption almost every single week to see whether the products of your reactions are what you think they are. You look for bonds present, you look for bonds absent based on the energy that's absorbed, and you can help identify your compounds that way. Any other classes you'd recommend, Dr. Holcomb?
Well, if you're just starting out in your chemistry adventure, you could start out with Chem 1010, which is the introductory to chemistry. That will give you all the tools that you need for Chem 1210, the Gen Chem course, that covers substantially more.
Absolutely. Chem 1010 has a good background, a good overview of everything you need to do well and ace Chem 1210 and all subsequent classes.
What is the distinction between like when a bond is broken and when there's just motion?
Actually, that's a great point. You know, I have a lot of slides, and I did not get to most of them. So let me show you one on energy involved in chemical reactions. Chemical reactions require that bonds break, which takes a lot of energy. As we saw, you need to go out of an energy well to get those atoms to move away from each other, which means we have this amount of activation energy. But then if you're going to form new bonds, you can come back down in energy, releasing some amount of energy. So this is what we call, oh, you can't see my finger. This is what we call an activation energy in order for a chemical reaction to proceed. Bonds break and bonds form, resulting in some change in energy between the starting material and the products. Did that answer your question? Can I answer it better?
I'm sure that there's a lot more that goes into it.
So if you provide enough energy, you can break a bond. But then that bond might just reform because those atoms will want to move back to a lower energy. So unless you can provide them with a new bond to make, then they might go through a chemical reaction or they might just reverse themselves. For instance, if this was, I think my thing's getting darker. If this was our bond energy and here is where our bond is dissociated and our atoms are not bonded, you'd need to maintain this energy or higher to make sure that that bond doesn't reform, or at this tipping point, the bond may reform or a new bond may form. So you would need to create very high energy and maintain that very high temperature to keep a bond broken. Great question. Oh, we are past time. So any further questions? I'm happy to take them afterwards. Thank you guys very much.
Yeah, so just a few last words. This is the last STEM talk for this semester. We're going to have more in the next semester, so look forward to those. Our first one in the spring is going to be on January 27th. It will be about the physics and chemistry of breathing and how breathing works and how to most efficiently breathe. That'll be with Andrew Vogt. So please come to that. Please leave these outside the door so we can recycle them. Also, the attendance sheet is out there. If you didn't get to it, please put your name on it. And if you have any other questions for John, come up and ask.